Welcome to Professional Tutors, the British online school. We are a team of dedicated and qualified teachers here to help you reach your full potential. Hello, here we are again in, well, I say familiar surroundings, but it's slightly unfamiliar at the moment, isn't it? But all being well, we should be back soon. The reason I'm here is so I can demonstrate, as usual, which is why I do these videos, a practical situation. And what we've been looking at over the last 3 or 4 weeks is forces, different types of forces we've looked at. And the first time that we discussed forces, we looked at magnetism, and we looked at magnets attract or they repel, and we also made an electromagnet. And the electromagnet is over here, but the electromagnet picked up the clips because we put an electric current through the copper wire that goes around the nail. And some of you designed your own and sent them in. Fantastic. I've really seen some tremendous work. I've written some of the key words down that we've been looking at along the way, and they are forces, push, pull. Now, you've known for a few years now that forces are either a push or a pull. Then we did magnets, like I've just mentioned, attract and repel. I've probably missed something out here, which I can put in. What do you think they are? North Pole and South Pole. There we go. And that covers the magnetism. We also, last week, discussed friction. Now, can you see how this list's building up? I will upload this list onto Google Classroom for you. Now, friction, as we discussed last week, is when two surfaces meet. And a problem can be that things can get hot, they can overheat, or we can use it to our advantage, like I said last week with brakes on a car, to stop the car. So we talked about friction. This week, I'm going to discuss with you gravity. Now, gravity is what pulls us down onto the earth. We exert a force onto the ground, and it's due to gravity. If you jump out of an aircraft, gravity will pull you to the ground. That's why people use parachutes, otherwise they'd just hit the floor. And the up force going up to the parachute lifts the parachute, and then it balances and starts to come back down. Now, I'll give you some examples of forces, up thrusts and down forces, in a minute. But firstly, I want to just discuss that forces are measured in newtons. Now, we use instruments a lot in science to measure things. For example, if I want to know the mass is the correct word, of this cork, I would use scales. And that is 2.57 grams. Right? Now, grams is what we use for describing the mass of something. Now, if I want to measure the length of something, I would use a ruler. For example, this block of brass is 5 centimetres long. Centimetres, so grams for the mass, centimetres for the length. Now, it's quite warm in here today. It's usually pretty cold, but it's quite warm in here today, and this is what we use to measure the temperature of something. This is a thermometer. Now, you've used some of these yourself. You've used them when we've heated up water, and when I've shown you the Bunsen burner and how it heats things up, and we've used these. You've made, well, they're being used a lot at the moment, taking people's temperature. If they're too warm, they might have a problem. And that's a thermometer. They're used in all kinds of situations. And that is measured in degrees Celsius. So let's do a recap here then. So degrees Celsius is the temperature. Length, centimetres or millimetres or metres or kilometres, they're the units for that. And grams for the mass. Now, I mentioned earlier to you gravity. And gravity is what pulls us down to the ground. Now, there is also something else here, and it's called upthrust and downforce. Now, the upthrust is what pushes up, and the downforce is what pushes down. Now, if those two are balanced, then something will stay where it is. Right? For example, if I was to put this brass in this water, you've looked at floating and sinking in the past, but this is explaining it in more detail. If I was to put this brass in the water, what do you think would happen? Do you think the downforce is stronger than the upforce? Because if the downforce is stronger, it will sink. So the downforce is considerably stronger than the upforce, so it's not balanced. Okay then, let's try something else. This is a block of wax. Now, do you think the downforce will be stronger? The upthrust force will be stronger, or do you think it will balance? Let's have a look. That's slightly more of a downforce than there is an upforce, because it's more or less below the surface. Look, can you see that wax there? So I would say that isn't really balanced. It's floating, but eventually I think probably we could be looking at that sinking eventually. And this is the thing that they have to take into account when they're making boats, ships, anything like that on the ocean. Now then, we'll take these out because then we can see better. So we've established that the downforce on that is stronger than the upforce. We call it upforce or upthrust, right? In fact, I'm going to write that on there next to upthrust so you'll know what it means. Upforce. We'll call it an upforce, right? There we go. So let's try something else then. What else have I got here? That is rubber. Now, do you think that the downforce will be stronger than the upforce, or do you think it will balance out? Let's have a look. Perfectly balanced. So the downforce is balanced with the upforce, and because of that, it is floating. This is how birds float. The hummingbird floats. It's a tiny little hummingbird. It spends most of its life flying rather than on the ground. And that will do this very similar thing. It hovers like that. So the downforce is equal to the upforce. And that's the same with floating and sinking. So let's start. We've established that that one's balanced. That would be, some of the boats are made of rubber, like they're called ribs, and they've got inflatable rubber on them, and they've got a rigid plastic middle, and they are what they use for rescue boats, and they're taking into account all these kind of materials that help it to float. Now here we have wood. Now I'm not quite sure what you think here. Whether you think that the downforce will be greater than the upforce. Let's have a look. Let's make some predictions. Well, I'm not going to make a prediction because I've done it before, but you are. There you are. That's more or less in the middle, which indicates that that piece of wood is completely balanced with the upforce and the downforce. Now, I've mentioned boats to you that need to be taken into account. So, there are other things. For example, if you want to get a helicopter off the ground, if you want to get an aeroplane off the ground, they have to create a massive amount of upforce, because that upforce has to overpower the downforce. So what it will do, these jets, these Eurofighters, they can take off a ship which is only probably just longer than probably from here to the end of the Tiger Turf, yet they'll take off into the sky with the jet engines because they're that strong and that powerful. A rocket, for example, doesn't take long before it's in space. Doesn't take long at all, because the fuel that they use creates such an upforce that it can blast its way through the atmosphere. Most of the rocket is made of fuel tanks, which they move off, get rid of, once they're out of the atmosphere. So, I discussed with you earlier, and I missed something out, and I'm going to mention it now, and that is how we measure force. Right? Actually, it's a good time to mention it now because we've just measured the upforce. And when you're looking at things like upforce of rockets, the torque in a car, the amount of power the car's got, they'll refer to newtons. Now, forces are measured in newtons, and the Newton scale is one of like this. Now, I can have a look on here. You've got 0 newtons to 10, so that's a 10 Newton meter scale. I can go, right, how many newtons will it take to pick up this chair? That's gone way past the scale. I would say that's about 15 newtons to pick up this chair. But a good way of demonstrating this to you is by using these masses. So if I put some mass on here, there we go. So a mass of 200, that's exactly accurate actually. A mass of 200 is showing 2 newtons on the scale. Can you see that? So let's put 3 on. Let's make a prediction. What do we think will happen if we put 3 on? There you go. And that is how we measure newtons. Now, let's just go over some of these key points again, because they are important. If we want to know the mass of something, we'll use scales to determine the mass. That's 2.56 grams. If you have a look. Okay. Now I could take that off and I could put something else on. And that tells me that block of wood is 47.87 grams. So the mass is measured in grams. Or in your case, or my case, or if you want to, you probably, if you go and have the doctors that take your weight, right, they take your mass, it'll be in kilograms for us as adults and children and, you know, as humans. Not piece of wood or piece of cork, that's in grams. But kilograms is 1,000 grams. Kilometres is 1,000 kilometres. So when you see that word K, it means 1,000. Right, so we've established then that forces are measured in newtons, after the man himself, right? And that's a Newton scale. Temperature is measured with a thermometer, and that's in degrees Celsius. Length, I mentioned that earlier, either centimetres or millimetres or metres. So that's the units we use for that. So let's have a recap then. We've talked about gravity being the pull that's caused by us on the earth. We exert a force of gravity on the ground. That can be overcome, that can be changed. We can change it by, for example, if we want to move something along, the force will have to give it that energy for it to move. For example, a car. If you turn the engine on and the engine starts, put your foot on the accelerator, you increase the amount of force and the car will move along. Now, we talked about balanced and unbalanced forces, didn't we, as well? Now, we said that this is unbalanced because the downforce is more than the upforce. We did that earlier. And we also said that this one was perfectly balanced because the downforce is equal to the upforce, so it floats. That's how we have to design boats. So they are equal forces, otherwise the boat would not sink. That's why we can make boats out of iron. I mean, the Titanic was made out of cast iron. It was made out of iron. Rivets were made of cast iron, some were made of steel, and that's how that was built. But it was designed in such a way that it managed to balance the downforce with the upforce. So the task I want you to do for me, these are the key words again. Let's go over these key words because this summarises the forces topic that we've been doing. So forces is the name of the topic. We know that it's a push or a pull. It's commonly referred to that, right? Magnets, right? Magnetic force is one of the forces. North pole, south pole, attract, repel. It's probably coming back to you now. Friction, we looked at friction, another force when two surfaces meet. I showed you last week that I needed to reduce the friction on the bike. That's why I was outside last week with a spray can of lubricant so it could ease the force and reduce the friction so the chain could go around. Today, gravity. When something exerts a force on the ground, it's said to be gravity. It's gravity what pulls it. Gravity controls the tides, pull of the moon and the planets. The planets exist because of gravity in the solar system. We're going to do the solar system a little bit later on because I want you to do a little project for me in a few weeks. Now, we also discussed upthrust and downforce. Now, in the case of this, my badly drawn rocket that I did earlier, the upthrust from these engines are phenomenal. If you look at NASA on YouTube and you look at the amount of torque and the newtons from those engines to get that rocket into the sky, it's phenomenal. You can actually, well, there's lots on there. When the space shuttle takes off, the force that's needed is incredible, and it's because of the fuel hydrogen that they burn. highly explosive, and that's what enables it to go. It's like a giant rocket that goes into the sky that you use at bonfire night, things like that. Now, where could we here on this rocket put upthrust, downforce, gravity, and friction? Where could we, on that rocket, where could we put an arrow to where there's going to be friction, to where there's going to be an upthrust? I'm going to do the first one. There's your upthrust. Maybe I should have done it the other way around like that, because it's going upwards, isn't it? So that's your upthrust. Like that. Your downforce is going to be there, isn't it? Because of gravity. So there's your downforce. Your friction is going to be from the air. Air contains particles, little bits of dust, all kinds of things in the air. That is going to give us our friction along here. Friction. Which is why a rocket has to be streamlined. If you think about a racing car, it's very, very streamlined so it can go through, cut through the air. Rockets have to be the same. That's why aircraft are the shape that they are, so they're streamlined. If they were shaped like that, the air would hit it like that and drag it back. It's called drag. So I've put those key points on there for you. Your task for today, I want you to design me on some paper, right, a rocket. I've done the outside of it. I've put NASA on there. Have a look at some NASA YouTube videos of the space shuttle taking off. And we'll get some ideas as well from the images. I want you to design me a rocket, but I've done the outside here and I've done the inside there. How are the astronauts going to live? Because they can be in space for some time. If you think of Tim Peake, he was up there for some time. Have a look, see how long he was there for, because I can't quite remember. But he was there a while, and they had to live in space. How do they live? How do they eat? How do they sleep? What do they do? We need to accommodate that. If you're designing this rocket for these astronauts, make sure that this is the inside, right? What I'm going to do with mine here, I'm going to say that's fuel. There, that's the fuel tanks. This will be the living accommodation here, and that's probably that bit there where the astronauts sit when they're flying it into space. That's why they're like that, lying down more or less, and then obviously when it goes into space it levels out. So that's them there. So what are you going to do for me then? I want you to tell me what's going to be inside. How do they eat? How do they sleep? How do they live? You're at home at the moment, eating, sleeping, living. How do the astronauts live inside there? I want you to design me this rocket this morning, and I want you to take some pictures of it, and then when we get back in this place, things get back to normal, we can then build a 3D model version of them, and we can have a look how they travel and things like that. So my task for you, I'll tell you again, I've labelled this, right, so you should have an idea of that now. You can stop the video anytime and go back, which is why I do this, to demonstrate practically in a lab how things work, rather than just a video. So, rather than just on Zoom, whatever. So, you're going to tell me, I want to see some really nice designs of how the astronauts live. I'll write that on this paper here. How do they live? What I mean by that is sleep. Where do they sleep? Eat. Do they cook like big meals for each other? Do they just wander around and cook and all this kind of stuff? How are they going to do it? So design me your own rocket. It can be any shape you want, but just think about the streamlining. And I'm looking forward to seeing some of the pictures, because as soon as we're back in this place, back to normal, then we'll make some 3D models of it. Good luck.